We don't have the sound online.
Yeah, that's the point.
Do you have sound now?
Yes, thank you.
Okay, thank you. Can I? Okay, finally. Okay. First of all, thank you all, and thank the organizer. I want to thank the organizer for having me here. I'm Stefano. I'm a postdoc in Merate near Milan, and today I'm going to talk about the radio afterglows of gamma ray bursts. And also, before starting, I would like to thank all my collaborators. Some of them are listed here, but there are many, many more that helped me a lot during these years. So the outline of the talk will be the following. Oh, Benito is online. So the outline would be the following. I will first introduce gamma ray burst. I know that we already know everything thanks to Maria Grazia, but I prepared a slide and I'm not going to change them. So I'm going to talk about gamma ray burst. Then I will provide you with some examples of radio observations of gamma ray burst in which actually radio was fundamental to provide information that could have not been obtained with any other methods or bands. Then we'll do the same for the gravitational wave events, actually event, there's only one. And I will then talk about the prospects and future outlook for the radio observations of both GRBs and gravitational wave counterparts. And I will leave you with my conclusion with the take-home message. So let's start. Gamma ray bursts are the most powerful explosions in the universe. They are observed as brief flashes of gamma and X-rays that can last from a fraction of seconds up to hundreds or even thousands of seconds. And in this brief amount of time, an enormous amount of energy is released. We are talking about an isotopic equivalent energy of the order of 10 to the 48 to 10 to the 54 ergs. And when they occur, they can outshine the entire gamma ray sky. As you can see on the right panel of the slide, when a gamma ray occurs, it can outshine the entire gamma ray sky. These are real data from BATSI. According to the duration, we can actually divide them into long and short, where long GRBs are thought to be due to the collapse of a single massive star, such as a Wolf-Rayet star, while short GRBs are thought to be due to the merger of two neutron star and neutron star and black hole. Regardless of the different progenitor, a black hole or a highly magnetized neutron star will eventually be produced. This central engine will accrete material and launch two relativistic jets. In the standard model, multiple shells are rejected, and when a faster shell catches up with the slower one, inner shocks arise. Here in the movie, the electrons are accelerating, they produce gamma and X-rays through synchrotron emission, and this is what we call the prompt emission, and was that brief flash. Okay, sorry. The outflow continues to expand. It sweeps up material from the surrounding medium and interacts with it through external shocks, producing the so-called afterglow emission that is caused by two shocks, actually. A forward shock that is propagating in the surrounding medium, and the reverse shock that is propagating backwards into the ejecta. And these afterglow emission can be observed from the very high energy down to the radio band. This is what I'm studying, the radio observation, the radio emission of these afterglow phase. So before moving on, providing you some examples of radio studies, I have to do another brief introduction on why it is worth studying GRBs in radio, and I've gathered here three main reasons. The first one is that the emission at these wavelengths is slowly evolving, is slower with respect to the X-rays and optical, and therefore it's in principle easier to distinguish between different emission mechanisms, such as the reverse and forward shock I was mentioning before. Also, since this is synchrotron emission, it is moving towards lower frequencies in time, and therefore in these bands we can actually see the break frequencies passing by, and we can constrain in a better way all the microphysical and global parameters of the emission. Then we can perform very long baseline interferometry so that we can put antennas all over the world in order to have a milliarc second resolution. And with this milliarc second resolution, we can actually we can measure the viewing angle and the jet opening angle. We can have some hints on the geometry of the jet, if it is a structured jet or a choked one, as we will see later on in the talk. And we can also have some hints on the dynamics. This is always sliding down. Okay. And finally, as the radio emission is heavily dependent on the surrounding medium profile, we can have some hints on the progenitor's nature. So imagine that we have a star producing a long GRB, but before producing the GRB, we expect the star to produce a strong wind. And therefore, when the star explodes and launches the GRB will expand in a wind-like environment. On the other hand, for merger events, we expect them to be embedded in a homogeneous surrounding medium or an ISM. And therefore, by studying the radio emission, we can actually have some hints on the surrounding medium, and from that, we can actually constrain the progenitor's nature in a way that go beyond the usual classification that we do based on the duration only, that is not up to date as recent events showed us. So a general view, the most comprehensive study on radio observations was performed by Chandra and Frey in 2012. You can see here the luminosity as a function of time, so that how the emission is changing in time. All these lines are, for each line, there is 1 GRB. These are only detections. The red line is the median of all the detections. They are not including here their upper limits. And the main point here is that is not the radio luminosity, but is the fact that they found that while for X-rays, we have 95% of the detection rate when we observe the GRB in the gamma rays. In optical, we have 70%. In the radio, we have 30%. Now, I put an asterisk here because it's actually most recent studies says that this is around 50 now, 50%. But still is way lower with respect to the X-rays and optical. And this is mainly because radio facilities are less sensitive. So I'm now giving you some example, actually 1 GRB, which is the brightest of all time, 2210 This was the brightest ever recorded, and it happened the last year of my PhD. That made me really, really lucky, I would say, because I made a paper on it, the best actually. And to give you an idea on how powerful this burst was, do I have a pointer? Thank you. It's too late to ask, but thank you. Yeah, probably it's better if I take the microphone. Well, anyway, yeah, I will do later. Okay. Yeah, thank you. No worries. So, okay. So here I'm showing you the count rates of previously well-known GRBs, actually 130427A. This one was the second, I think, brightest before the boat. And as you can see, the boat is orders of magnitude brighter and longer with respect to the previous one. And this is quite impressive. And since this was so impressive and so nearby, there was an extensive campaign from the very high energy down to the radio band. But of course, I'm focusing only on the radio band. And it's not working anymore. Perfect. Okay, I should use it. Okay. So here on the right, you can see the flux density as a function of time. We call these light curves. These are on the panel on the right. You can see that there are the light curves for each given band from 15.5 gigahertz to 0.15 gigahertz on the lower right. There are 3 interesting things here. The first one is that you can see that there is some variability, for example, at 5 gigahertz and at 10 gigahertz. And this variability cannot be ascribed to scintillation. I don't remember why, but in the paper there's written. And this is the first thing, because we do not expect scintillation, we do not expect variability from the standard model. Second thing is that if we take at a given time all the epochs and we plot the flux density as a function of frequency, we get the spectrum, and the spectrum is actually flat. For almost all the times, the spectrum is flat. It's getting dimmer and dimmer, but it's flat. And this is another thing that is completely not explained by the model. And the third thing that is the most interesting for me is that at 15 gigahertz, we can see this beautiful peak that is zoomed in on the left panel. And the peak is actually reaching 50 millijansky, which is a lot for those that are not familiar. So I guess almost everyone here. I'm usually dealing with something that is of the order of 150 microjansky, so 2-3 orders of magnitude fainter. So this was very impressive. And this peak was actually sampled in a beautiful way. And the important thing is that we ascribe this emission to self-absorption regime of the river shock. And this is actually, I think, the second time ever, or probably the first, in which we can actually see this regime for a river shock. And this was actually observed only in radio and only at these frequencies. So first thing, that radio is complicating things, and but we can actually discern between different components. So we can also use very long baseline interferometry, I was saying, and in this case, what we can actually see is the acceleration of the blast wave as an increase in the angular size of the emitting region. Imagine that we have here a black hole that is launching a jet, producing a blast wave that is pointing towards us. These two panels, perpendicular to the line of sight, are the representative, let's say, of two observations. And from the first observation to the second one, you can see on the map on the lower right that the emitting size is increasing in time. I think you see again, okay. And this was actually done for 221009A for the second time ever. Here you can see the projected size as a function of time. Each color is one frequency. Blue is 5 gigahertz, 8 gigahertz in purple, and yellow 15 gigahertz. The second thing is that this is a Bayesian plot, a violin plot. So we did a Bayesian fit. So the width of the colored area for each epoch at a given frequency is proportional to the posterior distribution we got for the size of the GRB using a Bayesian fit. So we got the data, we perform a fit with the Gaussian, we get the full width at half maximum, which is comparable, let's say, with the size of the GRB. There's a constant, but okay, that's not important. And since it's a Bayesian fit, we don't get a single value with an error, but we get a posterior distribution. And this posterior distribution is proportional to the width of the colored area. And therefore, the better the constraint, the narrower the distribution. So in the two cases in between, at 15 and 5 gigahertz, this is quite good. While for the first blue epoch, for example, and the last yellow, you can see that we put upper limits to the triangles because the distribution is very bad. Then when we do this for all the epochs at all frequencies, we can then perform a Bayesian fit with a single power law to see how the size is changing in time. And this is the dashed black line. And in the inset, you can see the posterior distribution for the slope of this power law. And we had more than 4 sigma evidence that the slope is larger than 0, so that the GRB is actually expanding in time. And with the value A we derived of 0.7, we can actually, we did it in the paper, we can actually compare this value with the prediction from different models. So I'm now going to talk about the gravitational wave event again. We all know 1708, 17A, of course. So here again, I'm showing you how radio was really fundamental in this case. There's no reason to say something different in this case, because we can see again the flux density is a function of time. So that again, light curves. The points are data from the radio in gray. This is brown, red, and yellow to optical and X-rays. The curves here are the modeling light curves. And as you can see, there are two types of curves, the solid line and the dashed line, and they both can fit the data. The solid line is representative of these model on the left, so that the structured jet, so that the jet with the structure within the jet opening angle, as seen as slightly off axis, while the dashed line is representative of a choke jet, so that's a quasi-spherical jet that has a radial velocity distribution. And with the light curves and spectra only, we cannot tell the difference, so we really miss the geometry of the jet. So the first important thing in radio that was done was the polarization measurement. Here you can see the linear polarization fraction as a function of time. There was only one upper limit here, but this was very important because these lines here are what we expect from a structured jet, so that on the left, while this dotted line here is for the quasi-spherical emission, and the Corsian collaborators actually could rule out most of the configuration of the magnetic field for the structured jet, while for the quasi-spherical one they did not, because it's not enough, but we don't care because we will see later on why. So why? Because if we do VLBI in this case, and we are in a slightly off-axis case, we don't see only the expansion, but we can see also the displacement of the center of the emission. I hope that this is quite clear, this animation here, but from the first to the second observation, we see a displacement that is observed in the map. And this was actually done for 170817A. Here I'm showing you two maps that are superimposed, declination and right ascension. These are radio map with VLBI. The first one is at 75 days post-burst in black. This is a contour plot. The second one is in red at 200 30 days, and as you can see, the center of them ruled out the choke jet scenario. But the final evidence was performed by Giancarlo Ghirlanda and collaborators with global VLBI, with an observation in between the two we have seen, so that the 200 days in which they could actually constrain the size so well that they could compare what they observed with what the models predicted, and they could actually rule out completely the choke jet scenario. So in radio, we can actually, with radio only, we could actually say that, first of all, this is a structure jet. Second, that the magnetic field parallel to the shock front was very low from the polarization measurement. And this was actually also the first proof ever that successful jets from a binary neutron star merger are a thing, because this was posited in the 80s by Eichler, but it was confirmed only by VLBI 40 years later, which is quite powerful, I would say. So now the future. Maybe you have heard about these square kilometer array, or SKA. This is a super facility that will be, is being built actually in South Africa and Australia. In South Africa, we will have 197 dishes of 40 meters each, working between 350 megas and 15 gigahertz. While in Australia, we will have more than 130,000 antennas of 2 meters each. I've seen them. They are actually metallic Christmas trees. And actually, when I saw them, I suggested them to put on Christmas, to put some Christmas balls. But on 130,000 antennas, I don't think they're going to do that. And they are going to work between 50 and 350 megahertz. The other very important facility, but this is actually being debated, is not funded yet, not totally at least, is the next generation VLA. This is going to be built in US, Mexico, and Canada. And it will have three main arrays. One that is 214 antennas of 80 meters each. They are the red points. Then the short basin array, that is these small circle here in New Mexico, that is 19 antennas of 6 meters each. And then we have the long basin array, that is the most interesting for me at least, which are 13 antennas of 80 meters, which are the purple points. Actually, they are not 30, I don't know why. Anyway, so these two facilities will heavily impact the science we can do on GRBs, of course. I have to do a disclaimer before going on, because for SKA at least, the only study that was done on the impact of SKA on GRBs was done in 2013 by Giancarlo Ghirlanda, and at those time, the SKA was a bit optimistic. Now the project has been downsized many times, so these numbers you are going to see are a bit over-optimistic, but the SKA2 configuration, which is the one they were calling at those time, now it's not called like this anymore, but it's very close to what they want actually to achieve. But I have to say that this year there was a call for a white book on for SKA, and they are actually working on these matters to update these values. So anyway, we should pass from 30% to almost 100% of detection rate at the peak time, so that whatever we observe at the peak time, we detect it. Here on the left, you can see the peak flux density is a function of time of the peak, so that we have the afterglow that is passing in our bands. It's peaking, and we take the peak and the time, and we plot it. The red dots are the real data they had at in 2012, more or less. The blue triangles are the upper limits at those time, And as you can see with SKA and GVLA, we should see everything. The gray dots are a synthetic population of GRBs by Giancarlo. So what we expect from every GRB, I would say. We should also pass from less than 15 to almost 50% of detection rate at the transition time, so that when the GRB becomes non-relativistic. This is very important because from that point on, the blast wave is described by a set of equations that is independent from the relativistic case, so we can have an independent way of estimates the energetics, for example, and we can perform calorimetry. Also, what I'm mostly interested in, it's not working. I should do this, okay, is to combine the super facilities with longer baselines, so we can do what we did for 1708, 17A, and for 2209A for almost every GRB that has enough signal-to-noise ratio, not only twice every 20 years. And of course, we can study the unknown, as with gravitational waves and GRBs, we have something new every year, I would say. Finally, for the gravitational wave counterparts, I'm choosing here the Einstein telescope era. This is because for 05, they told me that it's going to be almost the same as 04, at least for the counterpart in radio. So I'm showing you here the cumulative distribution as a function of the redshift for the gravitational wave and their counterparts. On the left, you can see binary neutron-star merger. On the right, neutron-star black hole mergers. So it's a quite complicated plot. I've studied for a week and I still have some doubts on it. So don't be too harsh on me, please. So the cumulative distribution are always really, I don't know. I don't get them. So the gray line is all the predicted merger we should have, neutron star and black hole neutron star. The black line is what we expect to detect with Einstein telescope in the triangular shape. The lines, the solid and dashed line that are colored are for gravitational wave plus something else. So for example, in blue, the kilonova, in red, the afterglow in radio. So this is the radio one, is the solid red line here. But actually, to detect something, we don't need only to have something that has a flux density that is above our limit. We also need to localize it. Of course, otherwise we don't know where to look. And if we include the localization problem, we actually, Alberto Colombo and collaborators include these as a localization limit, so that 100 square degree, which is something that can be done in the optical, the tiling. If we include these constraint, we go to an order of magnitude less events. And so on. So we should have 3 neutron star merger per year that are also detected in radio, and nothing of black hole neutron star merger. But actually, this is a conservative number, of course, because they assume that the black hole is not spinning and the neutron star is not deformable. But if you include the spin and you make the neutron star a bit more deformable, you can achieve more or less an order of magnitude more. So we can expect from 0 to 1 black hole neutron star merger detected in radio. So to conclude, radio is really important for GRBs and gravitational wave counterparts, because we can actually we can complicate things, which is always very funny, but we can also discern between different emitting components, as for 2210 we can constrain the dynamics of the burst that is giving us complementary information, and we can also derive the structure, the geometry of the jet, and these are all information that cannot be obtained with any other methods or bands so far, and they are really complementary to the single analysis of light curves and spectra. So they are really very, very important to break the degeneracy in the modeling. And so my take-home message is very, very easy. Radio is fundamental to study GRBs, and with this, I will thank you for your attention, and I'm happy to take your questions.
Susanna.
Thanks a lot. I also think that radio is great. And I have a comment and another common question. So the first comment is that just to say that the plot you show for the gravitational wave counterparts in ET, one of the major limitation is really the localization that lower down your numbers, and that so those numbers, just to give some hopes here, can be higher in case we have ET plus C, because the number of well-localized event really increased a lot within this 100 degrees square. So this was the comment. Then
I think of 4 times, right?
Yeah,
if I'm not wrong.
yeah.
Something
So
like
per
4
year,
times
like,
more.
Tens,
Yeah, exactly.
per
Yes.
year is not bad at all. So my question comment is that I think that we will be in some situation, because this is the possibility to detect these sources.
Yes.
And since they are all from afterglow, they will peak very late, at a late time that we don't know very well, because of many effects, and we have errors on the inclination angles and so on. So I really think that for most of them, there will be only radio where we can detect the counterpart. I will explain why. The optical is not the best one. And then we will have maybe some points at times that we don't know. I mean, we don't know when to look for them, more or less. And maybe they are faint, so we'll have just a few points and not enough variability in the radio to ascribe them to afterglow counterpart of axis afterglow counterparts gravitational waves event. Also because the region will be quite high, so difficult. So the detection, I think, is promising. The identification, I think, is more difficult. So I don't know if you have some comments, things to say in this perspective.
Yeah, that's a very good point, actually. So yeah, if we have the gravitational wave, then it's a bit better, I would say. If the we need the localization. That's the point. I can answer whatever, but the point is that we need the localization, because 100 square degrees in radio is too much. So we always need the optical, but if the optical is not the best one to do it, we
think that with some spectral information of the radio, you can see something.
Yes, in principle, yes, because you can still trace the afterglow emission, so you can always say something. Actually, if you don't see probably only if you don't see a single power law, but you see some break frequencies, it's easier. It's hard to distinguish between GRB afterglows in radio only with other transients. That's true. I'm not hiding it. That's completely true. But yeah, from the spectral information, we should. I don't know if we can actually say that that's a GRB, because there are already some studies on, for example, on radio of an afterglows, right? But you can never tell if it is an afterglow or not. You can say, okay, it's possibly of an afterglow, but with radio only, you cannot. You always need everything.
Well, people think about other questions. I'm following up on this. I mean, your cut on the localization is based on the gravitational wave data alone. Right?
Yes.
But on this plot, at least, and we'll hear about that later on, the fraction of events where you identify the kilonova is quite high. And once you identify the kilonova, you know where to look in radio. So couldn't that help to boost your efficiencies of the radio detection as well?
Yes, here it's not shown the situation of kilonova plus gravitational wave plus afterglow. So yes, in that case it should be higher, because we know where to look. But the main point here for the afterglow, in radio is that it is limited by the selection they did. So that 10 microjansky. That's the real point. So we don't have many, not only because of the localization, but mostly because the sensitivity is not as good as X-rays and optical. With the other two facilities, we are actually working on it to see how the NGVLA and the SKA, because they will work at the same time of Einstein telescope, how they can actually see this afterglow. Also because the 10 microjansky for the NGVLA is like roughly almost 100 signal to noise ratio, so we can actually take a tenth of that. one microjansky, which is increasing a lot the number of detections. So
Silvia?
a lot of questions.
Hi, thanks. I'm extremely ignorant in radio, so I really appreciated this talk. And here's my ignorant
Thank you.
question. SKA, is it just looking up, or is it kind of points? And like what kind of delays will you have with SKA observations of, let's say, a GRB or a gravitational wave counterpart?
Okay, that's actually a good question because because SK okay, sorry, I need to use this. So in Australia, it's not steerable. So you look at the sky and that's it. You can change the phases, so you can repoint in some way, and you can actually, let's say, you can repoint in a strange way. It's not that you change, like in the optical, that you move it. While in South Africa, you are actually moving the telescope. So these are antennas that you can actually move. So yes, actually SKA will be mostly devoted to do surveys, which is really important for the off and afterglow and so on and so forth, while the NGVLA will be mostly working on, on proposals, let's say, not on surveys. So yes.
Thanks a lot. Other questions? Go ahead.
Yeah, when you showed the boat and you said the radio, you had some fluctuations towards the end that not scintillation, don't really expect. But could that be some sign of changing interstellar circumburst medium, or is that also not the right size?
Yes, it could. Yes, it could. So in the paper, I think they Lauren wrote feed the data with a 3-component shock, so that she assumed that instead of having 1 shock, we have 3, or instead of 2, we have 3 actually. And but the variability is, I think there is a discussion on the paper, but I don't actually remember. It was 1 year ago. So, but yeah, the variability could also be due to the different clouds of surrounding medium. Yes, we don't know. Honestly, I'm a bit pessimistic, and I think that it's only because of systematics between. But that's another point. She doesn't think the same. So.
All right. Thanks a lot. And